Technical coding interviews often feel like a test of infinite trivia. Candidates stare down thousands of individual algorithmic problems, assuming each requires a unique, bespoke solution. Attempting to memorize thousands of individual solutions is mathematically impossible and strategically flawed. Advanced coding challenges evaluate your capacity for algorithmic pattern reduction, the ability to map a novel prompt onto a known mathematical structure. Success comes from stripping away the superficial details of a prompt, whether the problem describes scheduling meetings or routing flights, to reveal the underlying structural template. We are going to deconstruct the specific core patterns that reliably reduce exponential time complexity down to linear efficiency. This structural recognition is the fundamental prerequisite for engineering highly scalable, distributed production systems. When moving from a single server environment to a hyperscale data center, data volume dictates performance requirements. We measure this scaling using Big O notation. Big O provides an asymptotic upper bound on an algorithm's growth rate, stripping away hardware specifics to show how performance degrades as input size approaches infinity. This line graph maps algorithmic complexity curves. At the bottom, we have constant and linear time, O of 1 and O of n. Above them, quadratic and exponential curves, O of n squared and O of 2 to the n. For small inputs, raw hardware processing power can mask the inefficiency of an O of n squared algorithm. The CPU simply brute forces the calculation. But as the input size reaches 1 million elements, that O of n squared curve spikes vertically. A nested loop algorithm that takes milliseconds for 100 items will require days of compute time. To bypass these computational limits, engineers use the space-time trade-off. Optimization usually involves allocating auxiliary memory. By storing the current state of data in a secondary structure, you eliminate the need to repeatedly scan the input with nested loops. Respecting these asymptotic limits ensures that distributed data pipelines continue functioning under massive scaling pressures. A frequent constraint in data processing is finding a specific, contiguous property within a larger sequence of data, like the longest substring without repeating characters. The naive approach to this problem uses a nested double loop. Two read heads check every possible substring combination, constantly resetting to the beginning for each new starting position. This forces the algorithm into an unsustainable O of n squared time complexity. The system repeatedly reevaluates characters it has already processed. The sliding window pattern solves this optimally. We establish two pointers, a left and a right bracket, starting at the first index. During the expansion phase, the right pointer aggressively moves forward, consuming new data until a condition is violated, in this case, encountering a duplicate A. The algorithm then enters the contraction phase. The left pointer shifts forward to drop the first A, instantly resolving the violation and shrinking the window to a valid state. Mathematically, this guarantees that each element is visited at most twice, once by the right pointer and once by the left. The execution is locked into strict O of n linear time. This abstract pattern translates directly into developer productivity tooling. Engineering teams deploy sliding window algorithms to analyze CI/CD logs, calculating rolling time windows to instantly detect spikes in error rates without reprocessing the timeline. By leveraging the monotonic property of contiguous data, real-time log analysis systems process massive data pipelines without latency. Another common architectural constraint requires finding pairs of independent, non-contiguous elements that satisfy a specific condition. This is illustrated by the classic two-sum problem, where an algorithm must find two numbers in an array that add up to a target sum. Instead of sequentially searching the array for a matching number, the optimal approach calculates the mathematical complement of each element and stores it. Here, the system reads 2, calculates that it needs 7 to reach the target 9, and stores that state in a hash map. When the read head reaches 7, it checks the hash map. The lookup takes O of 1, or constant time. The complement is found, and the execution halts. Utilizing O of n auxiliary space for the hash map eliminates the nested inner loop. This specific memory trade-off scales up to govern massive system architectures. Combine a hash map with a doubly linked list, you create an LRU cache. It stores frequently accessed data and evicts the oldest entries. The O1 lookup demonstrated in a basic coding test uses the exact same mechanics that ensure high-speed API response caching in production environments. The most complex algorithmic hurdles involve optimization problems containing overlapping subproblems. We see this in the knapsack or coin change problem archetype. where an algorithm must test different combinations of inputs to find the most efficient path to a target amount. A naive recursive approach forces the CPU to calculate the exact same branches multiple times. This redundancy creates an exponential O to the 2n timescaling, causing the system to stall even on small inputs. Dynamic programming systematically eliminates this computational redundancy. Instead of branching infinitely, we use an array to store intermediate results. Implementing this requires a strict state definition. You must determine exactly what value each index of the DP array represents. For example, the minimum number of coins needed to reach a specific subamount. Next, you establish the state transition. This is the mathematical formula detailing how smaller, previously solved subproblems combine to build the optimal solution for the current index. By tabulating the answer iteratively, you collapse an unworkable O of 2 to the n recursion tree into a highly manageable O of n multiplied by the target execution time. This iterative state management is the mathematical engine for high-scale resource allocation. In cloud orchestration, the target amount is a cluster's available capacity. By treating each new build agent as a coin with a specific resource cost, the scheduler uses DP state transitions to update the global allocation map without recalculating the entire infrastructure for every new request. Dynamic programming provides the structural blueprint for executing optimal resource distribution under hard hardware constraints. Facing unseen algorithmic challenges under strict, high-pressure time limits requires a highly rigid and systematic methodology to succeed. The PACER framework, problem, analyze, construct, execute, review, provides a universal attack plan. In the analyze phase, engineers map the data topology and identify specific constraints before writing a single line of code. During the review phase, the candidate explicitly calculates and defends the space-time complexity trade-off of their constructed solution. Technical coding challenges are objective tests of constraint resolution. Recognizing these abstract patterns allows engineers to map mathematically proven optimizations directly onto real-world high-scale systems. Mastering these foundational, primitive mathematical templates is the only true path to ultimately mastering complex, macro-level system architecture.